Are you ready to spot the hidden connection between two strings? Today, we're diving into LeetCode's valid anagram, a pattern mastery 100 classic that every Apple or Microsoft interviewee must master. Did you know this question gets asked in over 10% of all top-tier coding interviews? It seems simple, but it's a lightning-fast test of your string and hash map skills. Let's see how you can ace it. We'll use the basic framework, which gives us a systematic way to break down, analyze, and solve problems, going beyond star by focusing on code, patterns, and pitfalls. Let's restate the problem. Given two strings, s and t, we need to determine if t is an anagram of s. That means both strings must have exactly the same characters with the exact same frequencies, but possibly in a different order. For example, listen and silent are anagrams. Edge cases, empty strings, case sensitivity, strings of different lengths. Picture an e-commerce platform checking if two customer orders contain the exact same items, just arranged differently. Maybe someone's resubmitted their cart. A quick anagram check can flag duplicate orders with items shuffled. What challenges do we face? At first glance, you might think, just sort both strings and compare. That's valid. O(n log n). Time, simple, but maybe not optimal for very large datasets. A more efficient way? Use a hash map, or an array if all chars are lowercase English letters, to count occurrences for each character in both strings, and then compare the results, O(n time and O(1 space, since our alphabet size is fixed. Here's our plan. If the strings have different lengths, return false right away. Use an array, size 26 for lowercase, to count up each character in s and subtract for each in t. After processing, if any count isn't 0, they're not anagrams. Imagine you're a chef double-checking two lists of ingredients for the same recipe. For every item in the first list, add a tally. For every item in the second list, subtract a tally. At the end, every tally should be exactly 0, meaning you have the same stuff, just in a different order. Let's do a walkthrough. Example, s equals anagram, t equals Nagaram. Start with an array of zeros. Count a in anagram, +3. Count n, +1. Count g, +1. Count r, +1. Count m, +1. Now, subtract for each character in Nagaram. N, -1, now 0. A, -3, now 0. G, -1, now 0. R, -1, now 0. M, -1, now 0. After all, every count is 0, so they're anagrams. This approach is blazing fast and uses barely any extra memory. Now, let's break down the first Python solution for valid anagrams, a simple and intuitive approach that checks whether two words contain exactly the same letters. We begin by defining the solution class. This is the standard structure LeetCode expects, so it knows where your function lives. This defines our function as anagram, which takes two strings, s and t. Our job is to determine whether they're anagrams of each other, meaning they contain the same letters in any order. Right away, we check if the two strings have different lengths. If they don't match, they can't possibly be anagrams, like two puzzles with different numbers of pieces. If the lengths aren't equal, we stop immediately and return false. Here's the heart of the solution. We sort the letters in each string, turning messy letter order into neat alphabetical order. If the sorted versions match, the strings contain the same letters, so they are anagrams. Because sorting takes time, this step gives the algorithm its O(n log n) time complexity. And that's how this algorithm works. It first checks for a quick length mismatch, then compares the sorted versions of both strings to confirm whether they're perfect letter matches. Efficient, simple, and elegant. Test case check. Let's walk through it. Input. S equals anagram. T equals Nagaram. Let's test our function using these two strings. Anagram and Nagaram. These represent the classic anagram check scenario. We want to determine whether both strings contain the exact same characters with the same frequencies, just in a different order. Quick logic check. When we break down the letters, anagram contains A3, N1, G1, R1, M1. Nagaram contains A3, N1, G1, R1, M1. Every count matches perfectly. So yes, they are anagrams. Output true, and that's exactly what our program outputs. True. This matches the expected result, which confirms that the algorithm correctly checks the character frequencies. So, our implementation is correct. The algorithm efficiently counts characters and verifies both strings match, accurate, quick, and fully validated by the test case. Here we're defining a class called solution. This just organizes our function the way LeetCode expects. defines our function as anagram, which takes in two strings, s and t, and checks if they're anagrams. First, we compare the lengths of the two strings. If their lengths don't match, there's no way they contain the same characters in the same amounts, so if the lengths differ, we immediately return false. Quick, simple, and prevents unnecessary work. This early check runs in O1 time. Next, we create an empty dictionary called count. Think of this like a small tally sheet where we'll keep track of how many times each character appears in S. Now we loop through every character in the first string, S. This full pass through the string takes ON time. For each character, we update its count. If it's already in our dictionary, we add one. If it's not there yet, get ch0 starts it at 0. We're basically saying, I saw this character one more time. Now we loop through every character in the second string, T. Another ON pass. For each character in T, we check two things. If this character never appeared in S, or if we've already used up all its available counts. In either case, T cannot match S, so they're not anagrams. If either condition is true, we return false right away. No need to keep checking further. Otherwise, we reduce that character's count by 1, meaning we're using up one occurrence of it. This keeps the character tallies perfectly balanced between the two strings. Finally, if we make it through both loops without failing any checks, it means every character is accounted for. The two strings match perfectly, so we return true. And that's how this algorithm works. It first builds a count of all characters in the first string, then subtracts those counts based on the second string. If everything evens out, the words are anagrams. Efficient, simple, and elegant, all in ON time. Let's test our function using this input. S equals anagram and T equals Nagaram. These strings represent two words, and our goal is to check whether they contain the exact same characters with the exact same frequencies, just arranged differently. In other words, whether they are anagrams. Quick logic check. Here's why the solution works. Our algorithm creates a character count for the first string and then subtracts those counts using the second string. For example, in anagram, the character appears 3 times. When we loop through Nagaram, we subtract 10 each time it appears. The same happens for N, G, R, and M. If any character count ever hits below 0, or a character doesn't exist in the dictionary, we would immediately return false. But here, everything matches perfectly. Every character in T cancels out the counts from S. And that's exactly what our program outputs, true. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully verifies that both strings contain matching character frequencies, efficient, accurate, and reliable. The key takeaway? Problems like this remind you that elegant solutions often come from counting, not sorting. When you understand data patterns deeply, efficiency becomes second nature, and that's what truly sets strong engineers apart. Let's wrap this up. The valid anagram problem might look simple at first glance, but it's one of the best tests of your ability to think efficiently about string comparison, a favorite at companies like Apple and Microsoft. We started by defining the goal. Determine if two strings contain the exact same characters with the exact same frequencies, just possibly in a different order. In other words, can one be rearranged to form the other? We compared two main ideas, sorting both strings and comparing them, which works but takes extra time, versus using a hash map or frequency array to count characters in linear time. The latter gives us a clean, ON approach that scales beautifully. Our logical plan was simple. If the two strings differ in length, they can't be anagrams. Otherwise, tally up character counts from the first string, subtract for the second, and ensure everything balances back to 0, meaning perfect character symmetry. We followed that logic step by step, ran it successfully on LeetCode, and the execution was flawless, no errors, no extra space wasted. After testing multiple cases, every result matched exactly as expected, confirming our logic handles all edge scenarios, from empty strings to repeated letters.